So this talk has three authors, Anisa Tapper, and then Gillian Durand, as well as Maddie Ross, all students at St. Kate's. And the title of the talk is Lower Atmosphere Neutron Detection Using Personal Neutron Dosimeters. And I'll give you a 5-minute warning till the next talk through the chat privately to the speaker. Go for it, folks.
Hi everyone, my name is Maddie Ross and I'm a member of the St. Catherine University High Altitude Ballooning Team along with Anisa Tapper and Gillian Durand, and Anisa and I will be giving this presentation. This is the abstract for our research. This presentation will cover specific parts of our abstract and the analysis of the respective data, as well as how we collect our data. To collect data for our research, we use high-altitude weather balloons filled with hydrogen or helium gas. We send various sensors and trackers into the stratosphere via the high-altitude balloons. Figure 1 shows a weather balloon upon its ascent. The large white circle is the balloon. Attached to the balloon is the payload, and directly under the balloon is the parachute with a tracking device. The contents of the white box are identified by the arrow are shown in Figure 2. This box consists of Geiger-Muller tubes, also known as GM tubes, that count high-energy particles in the atmosphere, a pressure sensor, a temperature sensor, an Arduino board that is used to read signals from the sensors, a heater to ensure functionality of the materials as they travel through near space conditions, and a GoPro camera to provide visual data. Under the white box is the black Neutron box. This box contains the personal neutron dosimeter and will be explained later in further detail. Additional tracking devices that use radio signals and GPS are also attached to the payload under the Neutron box. To conduct our research, we fill the balloons with hydrogen or helium and send them with their attached payloads into Earth's atmosphere. The stratosphere and tropopause are identified in Figure 3 by the blue arrows. We primarily collect data in the stratosphere, which is a layer of Earth's atmosphere from approximately 14.5 to 50 kilometers above the Earth's surface. Our balloons reach a maximum altitude around 30 kilometers. Upon their ascent, our balloons travel through the troposphere, which is the lowest layer of Earth's atmosphere. Between the troposphere and stratosphere, our balloons pass through the tropopause, which is important to note because it is the boundary between the decreasing temperature of the troposphere and the increasing temperature of the stratosphere. Temperatures at the tropopause can reach -75 degrees Celsius. Figure 4 depicts a sample high-altitude balloon flight. After the balloon is filled with the lift gas, it descends into the troposphere, tropopause, and eventually stratosphere. While the balloon is in the stratosphere, it passes through the Regner-Pfotzer maximum, or RP max. This is the highest level of radiation and peak level of ion production. The balloon bursts when it reaches a high enough altitude, and it descends via its parachute. When it reaches Earth's surface, we recover the balloon and attach payload to gather the collected data. On the x-axis of this figure, you will notice the time after this particular balloon was launched, and on the y-axis is radiation exposure measured in micrograys. Micrograys are used when radiation is measured in relation to its effect on the human body. For our research, we measure radiation in the counts of high-energy particles, but for the purpose of this figure, these two measures of radiation are directly proportional. Through high-altitude ballooning, we are interested in gaining more information about galactic cosmic rays, or GCRs. GCRs are constantly colliding with Earth's atmosphere, typically in the form of protons, resulting in a cascade of high-energy particles called the cosmic ray shower. The unit of measurement used in data collection is counts, where each count is the detection of a single high-energy particle. In Figure 5, you will notice the components of GCRs. The electromagnetic component is made of electrically charged particles such as electrons. The hadronic component consists of tightly bound particles such as protons and neutrons. The mesonic component consists of smaller secondary particles. Muons are the main particle of the mesonic component. They are negatively charged particles that act similarly to electrons but have a much smaller mass. We are interested in further research regarding muons because they are the main components of secondary GCRs. The data we collect on high-energy particles has presented us with information about the RP max. The majority of the particle collisions we detect as a result of secondary GCRs occur within or below the RP max. The RP max was discovered by Erich Regner and George Pfotzer. In the 1930s, Regner and Pfotzer worked to find an effective method of measurement of the production of ionization deep underwater and in the atmosphere. They identified the location of the peak altitude of ion production, known as the RP max, which lies between 15 and 25 kilometers above Earth's surface and has been used to discover supernova as a source of GCRs. Regner's student Pfotzer is often entirely credited for the discovery of the RP max, because Regner was forced to retire early by the Nationalist Socialists in Germany due to his wife's Jewish ancestry. Only Pfotzer was consistently credited until recently. Overall, the RPMax provides us with important information about GCRs and the interactions that occur in secondary particle showers.
The cosmic rays cause particle interactions and are most intense at the entrance of the stratosphere and continue to lose energy as they travel towards the surface of the Earth. The hypothesis assumes that most particles are coming along the zenith, so there will be higher amounts of particle detection in the vertical direction at lower altitudes, and the horizontal direction will have lower amounts of particle detection and occur at higher altitudes due to scattering. The counts are detected in all directions. The omnidirectional orientation picks up muons and the alpha particles in every direction, but we are not able to determine the specific direction from where the particles hit the detector. It is expected that the zenith direction, which is the vertical orientation, will have the most particles because that is the direction from which they enter the stratosphere. The horizontal direction is expected to have lower particle amounts due to the particles traveling in the perpendicular direction due to scattering. Neutrons are a secondary product of collisions in the atmosphere, so it is expected to see them at lower altitudes. The bubble detector, called a personal neutron dosimeter, more commonly referred to as a PND, is used to detect fast neutrons during high-altitude balloon flights. The bubble forms due to the velocity of a fast neutron because the secondary particle shower allows energy to pass through the PND, which is converted to a gaseous phase and is trapped in the chamber. The dose range is in millirounds, which is a measurement of radiation. The PNDs were designed to be used by humans and were not meant to be flown into the stratosphere, but they work very well for high-altitude ballooning. Fast neutrons either perform elastic or inelastic scattering. During elastic scattering, the neutron bounces off the nucleus of the atom with no energy change, and the neutron changes direction. During inelastic scattering, the neutron bounces off the nucleus and loses some energy to the nucleus of the atom. The nucleus releases excess energy as gamma rays. When the neutrons hit the PND, the energy produced causes a bubble to form. There is currently minimal energy information, but we can state that an interaction did occur. Figure 12 shows the neutron payload, which requires a black background to reduce glare that is picked up by the GoPro camera, from the Arduino board in particular. The University of Minnesota Morris began this project, and the St. Kate's team has been able to collaborate with them on this. Video production plays a key role in neutron detection because the bubbles are seen and heard, so a high-quality video is necessary to extrapolate the data. The quality, exposure, and focal length of the camera were modified for this project to be able to see, hear, and count the bubbles that appear due to fast neutron collisions. 3 flights were conducted in the summer of 2019. A single bubble event had the highest rate of formation between all 3 flights, and the highest amount of bubble events occurred below 15 kilometers. In comparison, non-charged particles occur at lower altitudes than charged particles. During Flight 1, one of the GM tubes blew out in the vertical direction. The data confirms the hypothesis, which is that the counts in the vertical direction will be at lower altitudes and will have a higher number of particles being detected, and the horizontal direction will occur at higher altitudes and have a lower amount of particles being detected. In Table 1, the overall percentages confirm the hypothesis because around 72% of the bubble counts occur at or below 25 kilometers. Around 27% of the counts occur above 25 kilometers because the particle interactions occur on a continuum throughout the stratosphere, but the majority occur below 25 kilometers. Table 2 confirms the hypothesis because the horizontal direction occurs at a higher altitude than the vertical direction. The horizontal orientation should have a higher altitude because of the cosmic ray showers that cause particle interactions to occur. The particles will scatter in all directions, including upwards, which concurs with the hypothesis. The graph shows the counts from the PND in orange and the GM tube in blue. The counts taken by the RM60 GM tube were summed for each minute measured and were plotted against altitude with an overlay of the bubble detections, which showed a correlation between the data gathered. Neutral particle counts occur at lower altitudes than charged particle counts. From the graph, it shows that almost all counts for bubble detections occurred at or below 25 kilometers, which confirms the hypothesis that there will be a higher occurrence of particles detected at lower altitude. This also confirms that non-charged particles occur at lower altitude than charged particles, which is seen in the comparison on the graph. This is a still shot from a video of a bubble that formed during flight. The video will not be played during the presentation due to a time constraint, but it is available for viewing after the presentation. The bubble that appeared is due to a fast neutron going through the bubble chamber at a fast velocity. The members of the team determined the number of bubbles by recognizing when a bubble appeared from the visual data and by listening to the audio because the bubbles made a sound when they appeared. There is no altitude information from the footage, so the team was required to determine the altitude information from other data gathered and lining the times up.
In addition to the PND data, data was also collected from GM tubes. PNDs and GM tubes have been flown together during balloon flights to collect data about high-energy particles in relation to the RP max. GM tubes are ionization detectors that measure the charge produced during interactions between a radiation source and the detector. GM tubes give us information about the presence of high-energy particles, but we do not gain specific energy information and therefore cannot distinguish between high-energy particles. Identifying high-energy particle presence is still useful in collecting data surrounding the RP max. To collect data during high-altitude balloon flights, we use both RM60 and RM80 GM tubes. RM60 tubes can collect measurements in all directions simultaneously, while RM80 tubes are flat and primarily detect vertical measurements. Figure 16 shows RM60 GM tubes within a payload in the white boxes. Figure 17 shows a high-energy particle entering an RM80 GM tube. The GM tube is filled with argon gas at a low pressure because argon has a neutral charge. The high-energy particle that enters the GM tube is broken down to its positive and negative charged ions. The negatively charged ions are pulled to the negative electrode, which is outside of the aluminum tube, and the positively charged ions are attracted to the positive electrode, which is the central wire. When there is enough charge above a certain threshold in the gas, an electrical pulse is generated, and this pulse is read as one count of a high-energy particle. Because we do not gain specific energy information from GM tubes, we are hopeful to fly silicon photomultipliers, or SIPMs, to identify the presence of specific charged particles, such as muons. SIPMs are a good candidate for high-altitude ballooning research because they are suitable for high-speed distance measurements. A SIPM consists of an array of solid-state light-activated pixels, as seen in the circle in Figure 18. Each array in the SIPMs we plan to fly consists of 10,000 pixels. Light will only interact with one pixel at a time. When a pixel is activated, it will send a signal that causes the energy to change. More specifically, when a photon hits the pixel array, an electron and electron gap pair will move through the SIPM. The electron will separate from the electron gap and be pushed through the SIPM toward the negative electrode. As the electron moves to the right of Figure 19, it releases more and more electrons. Once it reaches the negative electrode, the signal is read out and a pulse occurs. We can count the exact number of photons that interact by the SIPM by the amplitude. From this data, we can determine the total energy of the pulse. When this is graphed, the counts can be identified, and the amount of photoelectron peaks can be converted to an actual energy and determine the energy of the event detected.
These are pictures of the actual detectors. These pictures are not to the same scale. The SIPM in Figure 19 is approximately able to fit in the mesh circle of the GM tube in Figure 20. The actual detector of the SIPM is within the white circle in Figure 19. The specifications for each device are listed here. The SIPM weighs 76 grams less than the GM tube, making it ideal for high altitude ballooning. The upcoming years will consist of testing out the SIPMs during flights, comparing how the SIPMs detect measurements to the GM tubes and PNDs, and preparing for the upcoming solar eclipses in 2023 and 2024. A majority of the neutrons detected pass through the PND at lower altitudes than the directionally measured RP maxima. The hypothesis has been confirmed because a greater occurrence of neutrons appeared below the main interaction layer in the upper atmosphere, which shows the importance of having charged and neutral detectors used in conjunction with each other to better understand the dynamic of the charged and uncharged particles in the stratospheric environment. Thank you to Dr. Damos, NASA Space Grant, and the UOM for this event.
Fantastic talk, Anisa and Maddie. Thank you so much. We are a little bit tight on time, so maybe I'd ask that while you unshare your screen,